Greetings, I am João Paulo Eguea, a Brazilian researcher, Bachelor and Master of Science in Aeronautical Engineering by the University of São Paulo, currently working on my doctoral thesis in the field of applied aerodynamics under Professor Fernando Martini Catalano supervision. I've been working on aircraft design and aerodynamics as part of my studies since I joined the Aeronautical Engineering College in the city of São Carlos. As a member of the Applied Aerodynamics Laboratory, I've worked on research projects in partnership with Boeing and Embraer, and as a graduate student, investigated aerodynamic solutions for improving aircraft performance. Such interest in working on technologies capable of reducing aircraft fuel consumption and emissions is strongly related to my interest in reaching a more sustainable society, a personal goal that is supported by the high commitment of the aeronautics academy and industry on constantly reducing the aviation market environmental impact. The aviation industry presents one of the more intriguing scenarios when it comes to environmental awareness. Despite the market's fast-growing rate before the COVID-19 pandemic, its contribution to CO2 emissions remains almost constant on 2% of all man-made emissions, according to research by the Carbon Dioxide Information Analysis Center. The academy, associations, and the industry presents great concern on developing regulations and technologies that may make the aviation market greener, being responsible for this scenario. Leading to this demand, researchers spend their time and brains on creating, testing, and developing new technologies and solutions for reducing the aviation environmental impact. At this point, one may ask, okay, we want to make aviation more sustainable, but how can we do that? As an applied aerodynamics researcher, I dedicated my master work to investigate the camber morphing winglet impact on a business jet fuel consumption, aiming to help the aviation industry to move towards a greener scenario by developing a technology applicable to future aircraft projects. Technology overview shows that the winglets are a well-known solution for aerodynamic performance improvement, being widely used in different aircraft categories. The idea of evaluating the aerodynamic benefit of applying a morphing system capable of adjusting the winglet section's camber according to the aircraft flight conditions is based in two cornerstones: improvement potential and feasibility. We expect that the camber morphing winglet concept would significantly improve the aircraft performance, reducing fuel burn without excessively changing the aircraft geometry and or affecting flight safety. Those concerns on the system design are fundamental for reaching a feasible and certifiable technology, increasing the concept application in the industry. The morphing winglet concept is capable of adjusting the section's camber for optimum performance by changing the leading and trailing edge angles. The investigated morphing winglet presented a rigid central portion between 25% and 75% of the section short length to keep the winglet structural box unchanged. Fixed leading and trailing edge plugs are used, ensuring that the camber changes would not result in unfeasible, wavy, or not smooth surfaces. Genetic algorithm was used for optimizing the winglet aerodynamic performance on a typical business jet mission by changing the section's camber for each flight condition, enabling optimum performance at the whole flight envelope. The optimization algorithm searched for the winglet configuration that minimizes the aircraft total drag at flight conditions determined on a flight performance simulation code. The BLWF code was used for evaluating the configuration drag based on the aircraft's weight and speed. The aerodynamics and performance simulations shows that the camber morphing winglet reduced 300 kilograms of the maximum range mission fuel burn. Also, the performance improvement enabled flying 700 nautical miles longer, or carrying 800 kilograms of extra payload on the maximum range mission with the same fuel burn of the baseline fixed geometry winglet. Those results exceeded the initial expectations and drew the Aeronautics Academy and industry attention to a feasible technology with great benefits on aircraft fuel efficiency. The results are promising, but an analysis of the actuation system weight and power requirements and its structural and aeroelastic impact is necessary for finishing the proof of the concept. Yet, the possible beneficial interaction between the morphing winglet and aircraft structures, like a load alleviation system, increases even more the enthusiasm around this technology. With such promising results, studies makes room for further investigation and system development on this concept, being a kickoff for developing this technology. This pitch is an invitation for discussing and creating a network so we can keep developing solutions that may contribute to make aviation and our society more sustainable. Thank you.